Okay.
Can you make the picture small?
Yeah.
Picture small. Let me just.
Good.
Okay. What's STAN? STAN is a state-of-the-art platform for statistical modeling and high-performance statistical computation. It works quite similar to Winbox and JAX, but the main difference between those program languages, the underlying MCMC sampling algorithm. In Winbox and the JAX, they use GIF sampling and the slide sampling to do the MCMC sampling. Instead, like we use a method called Hamiltonian Monte Carlo for Markov-Chain Monte Carlo sampling. The STAN package is built in C++, but we do not need any prior knowledge of C++ to use it. The STAN language can be accessed through a variety of interfaces, including R, Python, Julia, and Stata. Before we go to the illustration, let me show you how to install STAN. The easiest way to, I forgot to mention, like based on the background of our department, I will show you how to run STAN in R. Like how to install STAN, type STAN Bayesian in Google, and then you will get access to the homepage of STAN. And this homepage gives a very brief introduction of STAN and the function it provides. On the top, find the installation. Here, there is a list of STAN interface. Based on the list, we find that there are two interfaces that's related to R, RSTAN and command STAN R. Both are the package that can run STAN in R, but they are slightly different in the construction. The RSTAN interface is a in-memory interface to STAN, and it relies on R package like RCPP and inline to call C++ code from R, while the command STAN R interface is a lighter version. In general, what command STAN R did was that it will pass the input from R to command STAN, and then after the command STAN run the MCMC, it will read the input from command STAN back and pass it back to R. And after that, we can do data analysis. Because of the difference in the underlying structure, it's much easier to maintain the command STAN R package than RSTAN. Here, the command STAN R is the most updated version, and the RSTAN is nowadays outdated, so it might not include the latest development, the new method like developed by STAN development group. In this course, I highly
install the latest version.
It's not, it depends on the systems. If you use Windows, I don't think you can install it. And when I joined the Columbia and attend the STAN weekly meeting, in the very first meeting, they were complaining about the issue about like RSTAN installation in Windows. And they had a hard time struggling how to solve this problem. And I think this is some incompatible problem between the STAN library and the RCPP. And that's why our STAN is outdated. If we want to use STAN to do model fitting.
So you're recommending commands?
Correct. Command STAN is updated, but it's not available on CRAN. And that's why it's necessary for me to show you how to install command STAN R. Back to this page, click on command STAN R. On here, there's the code you can use to install command STAN R. Just copy this and open your R project or like R Studio and just paste it and click on enter. It will install the command STAN R package for you. The command STAN R is just an interface. To run the command STAN R, we need to install the command STAN, and this can be done by the command install command STAN. And there's a more detailed instruction about the options provided by like install command STAN on the page that I'm showing. If you have a laptop, you can try installing command STAN R and command stand. It might take a while for the computer to compile everything. But if everything goes smoothly, like you might be able to follow the data, like the code I'm going to illustrate. Okay, let me close this. In the talk, I will show you how to use STAN to do data analysis through a well-known example of the 8-screw problem. Let me first introduce the 8-screw problem. The 8-screw problem is a famous example of a hierarchical model in statistics. It's mentioned in Gelman's Bayesian data analysis book. The data is about a study for the education testing service to analyze the effect of special coaching program on test scores. In the dataset, there are 8 different schools, and they are experiments with a SAT coaching experiment. Anyway, for each school, we have the estimated coaching effect YJ and its corresponding standard error. And these data are obtained by an analysis of covariance adjustment. Like I skipped the details of how we generate the data, but you can check the BDA for like the more details about the data set. And here's a illustration of the data. The first column indicates a different school. The second column shows the coaching effect. And the third column is the standard arrow. And this, sorry,
Variance of the standard error.
yes, and this actually depends on the size of school, and it's pre-computed. It's not a hyperparameter in our model. The goal of the data analysis is to estimate the average treatment effect of a coaching program on student test score. For this data set, we build up a model as listed here. Here we define the theta j as the treatment effect in school J, and our yj is modeled by theta j plus the arrow term epsilon j. The epsilon j here follows a normal distribution centered at 0, and its variance equals sigma j square. And this is given in our data. The theta j here is the treatment effect, and we model it as a random effect. And jointly, all those treatment effect shares the same prior, which is a normal centered at mu, and it has variance equals tau squared. For the hyperparameter mu and the tau, we assign a normal prior for mu and a half Cauchy prior for tau. The half Cauchy prior here means that tau follows the Cauchy distribution, but we restrict the tau to be non-negative. The prior is selected based on the wiki page for choosing prior provided by the STAN development team. And you can find the link of this wiki page in this, in my HTML file. And I highly recommend consulting the result, this resource when you construct your own model, because it can provide valuable insight and it shows the best practice in Bayesian modeling. I can briefly show you these slides. For example, it provides introduce different type of priors, shows the general principle when we build a model and choose a prior. If we search half Cauchy, sorry. And we can find a reference, like a paper written by Gelman. In the paper, the paper discuss why we should use half Cauchy. And the 8-school example is also modeled in this item. The STAN modeling language uses a block structure to organize model code. The 3 main blocks in a STAN programs are the data block, the parameter blocks, and the model block. The data block is where we define the data that the model will be fitted. And this is how a data block looks like. Here, we can see that we need to provide the type of the data and also the restriction of the data. Here, we define the J to be the number of schools, and it's an integer, and it's not negative. At the end of our command, we need to use a semicolon, and this is required at the end of every command in Stan. To make a comment, we can use double slash, and this can make your code more readable. And our estimated treatment effects is inputted as a like one-dimensional array, and each element is a real number, and the sigma is another array, and the elements are a non-negative real number. The parameters block is where we define the sampling space. We can put the model parameters in this block, and like this is quite readable. But I want to point out that although this parameter block defined the sampling space, the actually sampling space might not be in the domain as indicated in this block, in this parameter blocks. The reason is that Stan will do some underlying transformation to change the support of the parameters to the real line to an unconstrained space. And that's why here we restrict the tau to be a non-negative value, but Stan will do transformation like log to change the support to the real line. Next is the model block. This block describes the model. The code is quite readable. The only thing I want to point out is that in Stan, the scale for the normal and the Cauchy, it stands for the standard error, standard deviation. It's not the variance. But in a multivariate normal, we need to input the covariance matrix. This is something when we use the function, please refer to the Stan user guides for the the details of each arguments. Now put all these blocks together, we defined a full Stan program. In the folder I prepared for today's talk, you can see there's a subfolder called Stan. Open it. The first file is the Stan program, as shown here. In addition to data, parameters, and the model blocks, Stan offers a wide range of program blocks, and this is a complete list of those named blocks. The functions block can define like a user-defined function, user-defined log likelihood. The transform the data can pre-process the data before we run the model fitting. The transform the parameter can do transformation of the parameter, and it also saves the MCMC sampling for the transform the parameter. The transform the parameter can be used in the model block. And the generated quantities block allows derived quantities based on parameters, data, and optional random number generation. All of the blocks are optional. In other words, you can just use the Stan to generate a set of data instead of doing model fitting. Like in this case, just I'm sorry, I forgot there is an example, but I can show you later. Now let's talk about how to fit the 8-school model in Stan. In my folder, I provide a R project and also a R program. Once you've installed command Stan R and command Stan, you should be able to run the program directly on your own machine. Here, we need to first load the library. If you've already installed command Stan, you can skip the second line. Next, generate the data. And then we can use the command Stan model function to compile our Stan program. The command Stan model function creates a command Stan model object from our based on our Stan program. And here, this code generates the object and name it as mode 1. If we run this model, we will see that our machine spends some time on compiling our STAN program and go back to our folder where we save the STAN program. This function will generate a compiled executable under the SAM folder of our STAN program. If we rerun this code, we'll find that as long as we don't adjust our STAN program, this function will not recompile our code. And this is a good way to save your time. And we can use the print method to check our STAN program. Next, we need to run MCMC sampling, and we can use the sample method to run the default MCMC algorithm. This is an example code for running sampling with command stan R. And the method has a variety of arguments that can be passed, but here I will introduce some of the most useful arguments. For more details, please refer to this link. The first argument is data. In this code, I just pass the data as the list of objects I've already defined in our program, but you can also pass of the data file that's compatible with command stan, or you can just put null or an empty list if the stan program has no data block. The seed is a random seed for the random number generation that's passed to command stan. I highly recommend you always set the seed because this can guarantee that your result is reproducible. Other people who run your code will get the exactly same result. Otherwise, there's no guarantee that every time when you run stan code, you always get exactly the same answer. The refresh is a argument that controls the number of iterations between printed screen updates. And the initial is not used in this demonstrate code because if you don't set the initial, stan will automatically generate prior initials for you. The underlying algorithm generate initials between interval from -2 to 2 for each parameters. But you can also set the bandwidth of the interval by a single real number passed to the initial. We can also set all the initials to a specific number and pass to the inits to tell the program where to find the initials for our program. Similar to data, we can also pass a list of lists that contains the initials for all or some of the parameter. And it's very interesting to mention that it's also possible to pass a function that can generate the initials for part of the parameters. Sometimes if we run with the default MCMC algorithm instead and we observe a lot of warning that occurs at the beginning of the MCMC, it probably means that the initials generated by stan is a very bad initials, and the acceptance rate or the convergence rate might be impact. So if we observe those warning message, I highly recommend you play with the inits argument. The chance controls the number of Markov chance to run. The default instance is 4. And the parallel chance controls the maximum number of MCMC chance. Next two arguments are the number of warm-up iterations and the number of post-warm-up iterations. When we do Bayesian analysis, we often need to resort to approximate algorithm like MCMC and variational inference. And the majority of those algorithms require a warm-up phase for the algorithm to reach the so-called high probability mass region where most of the posterior sample stays. If you check a typical MCMC chain for parameters like the log posterior, usually at the initial phase, there will be a very dramatic change in the scale of the iteration. But after the initial period, the MCMC chain will bounce back and forth within a relatively stable region. And this means that your this indicates that your MCMC chain might reach the high probability mass region and has a relatively good mixing. Next, I will talk about the argument for adaptation in STAN. And this is the algorithm that STAN provides during the warm-up period. Because in the underlying MCMC sampling, there are a lot of tuning parameters that can dramatically impact the sampling efficiency. But many of the users might not know how to tune the tuning parameters. So the STAN development team provides a lot of tuning algorithms to spare the effort of tuning parameters for the user. But to gain a deeper understanding of the argument for adaptation in STAN, I want to briefly go over the HMC algorithm and the underlying adaptation algorithm in STAN. As I mentioned earlier, STAN used Hamiltonian Monte Carlo methods to do MCMC sampling. The HMC algorithm needs to set at least 3 parameters: the discretization time, epsilon, the matrix n, and the number of steps takes. So in the updates of Hamiltonian Monte Carlo, we need to generate a trajectory that follows the Hamiltonian dynamics, but it's impossible to generate a continuous trajectory. So in the actual implementation, we need to use discretized approximation to approximate this trajectory. And how the resolution or the size of each discretized approximation is defined by this discretization time. And the length of the trajectory is jointly determined by this discretization time and the number of steps take, the L. So when we choose a very small discretization time, we can get a very accurate approximation of the Hamiltonian the trajectory that follows Hamiltonian dynamics. But of course, but it requires more computational cost. But when the epsilon is too large, the trajectory can can move very fast. But but the approximation will carry a lot of larger errors. So that's why it's important to tune this discretization time. And the n here, you only need to know that when the inverse matrix, the M inverse is a good approximation of the posterior variance, our MCMC sampling algorithm will be will have the best efficiency. In STAN, the warm-up periods has 3 stages. And in the first stage, it's called the initial fast adaptation interval. In the first stage, we let the MCMC chain run, and it will quickly move from our initial to the high probability mass region where most of the posterior sample stays. And in this period, the only parameters we adapt is the discretized time. And at the end of the initial phase, we actually assume that the MCMC chain has already approaching the high probability mass region. And then you can see in the second stage, there is a sequence of expanding windows. And this is where we adapt the matrix n. What STAN does is that we first run a short window, and within the window we fix the matrix. But after a short MCMC chain, we use the MCMC chain samples to update the matrix, the M. And then in the next window, we forget the previous sample and then run another short MCMC chain with the updated matrix. And After a fixed window, again, use the sample generated in the second interval to update the metrics. And after this sequence, we will update the metrics for our MCMC algorithm. And in the last stage, we fix the metrics and decide our final step size, which I mean is the discretization time. And here, these three parameters controls the width of each interval. The initial buffer, it controls the width of initial fast adaptation interval, and the term buffer controls the width of final fast adaptation interval. And the window here controls the initial width of slow adaptation interval. And these are the default value provided in STAN. And these are the arguments or the parameters that controls the step size adaptation. The last three are used in the dual averaging algorithm, and it's not STAN team does not recommend tuning the last three. But the delta here controls the target metropolis acceptance rate. This means that we want for each update, the probability of accepting the next proposal is around 0.8. Just imagine that when the acceptance rate is very close to 1, it means that the discretized approximation of the trajectory that follows the Hamiltonian Monte Carlo has a very good approximation. And in this case, when we increase the target acceptance parameters to be close to 1, this will usually generate smaller step size, smaller epsilon. And when we decrease this acceptance parameters, this will usually result in a larger step size. And STAN provides 3 different types of metrics. One is a unit matrix, which is diagonal matrix of 1, and the other is diagonal matrix, which means that when we adapt our matrix N, we adapt the diagonal elements of the N matrix. And the last is a dense matrix. I personally don't recommend that dense matrix because it can be very expensive for high dimensional model. But if your model is low dimensional and the fitting is very inefficient with the diagonal matrix, then maybe you can try the dense matrix. And now we discuss the adaptive algorithm for the epsilon and n. Now, what STAN do to choose the L? And this is this needs to STAN choose the L by an algorithm called no-Newton sampler, no-Newton Hamiltonian Monte Carlo. The paper here describes the underlying mechanism, but the paper is out of the scope of today's seminar. But I can give you an intuition of how this STAN choose L. In our STAN arguments, there is a argument called max tree depth. When we generate the approximation of the trajectory that follows Hamiltonian dynamics, STAN build up the trajectory by a binary tree. You can see the length of the trajectory increase exponentially every time we double the length of the trajectory. And this no-Newton sampler will stop expanding the trajectory once we detect a U-turn. In other words, the STAN will stop when the trajectory is far enough. And in STAN, the default value for the max tree depth is 10, which means that for each iteration, the L can be can grow up to 2 to the power of 10 minus 1. And this is a huge number. So sometimes when we fit the same MC algorithm in STAN, but we find that each update takes a very long time. then probably that's because like a stand is expanding this trajectory, but stand fails to detect a U-turn. So a stand keep expanding the trajectory, and it might waste a lot of computational power. Okay, so this is how stand choose L. This adapt engaged is is an option for choosing whether you want to do warm-up adaptation or not. And adapt delta is the delta that like I mentioned in the previous link, and it's the adaptation target acceptance statistics. The step size here just to set up the initial step size. And if we turn on the adaptation, it will be tuned during the warm-up. The metrics here specify the type of the metrics we want to use in the algorithm. I've already mentioned these 3 options like in the other like HTML. And now we can run the code and check the message report by Stan. You can see because we set the refresh to be 500, Stan reports the progress of the sampling every 500 iteration. And Stan also reports the beginning of the sampling process. Yeah. Okay. Yeah, it also reports the running time and some warning message. Next, I want to talk about the warning message and how we diagnostic the model fitting. As I mentioned earlier, all the MCMC algorithms require a warm-up phase, but we actually manually select the iteration for warm-up. In other words, there's no guarantee that our MCMC algorithm actually reach the high probability mass region. And it's also possible that during the tuning parameter, we fail to select a good parameter, and the MCMC algorithm can be very inefficient. So every time after we fit a MCMC algorithm, we need to diagnose the performance, the fitting performance. Here are some options that's provided by command stand are. The first one I want to mention is command stand diagnosed method. This method provides a summary of 5 different diagnostic metrics. The first is tree depth. The tree depth just to report how many iterations that hits the maximum tree depth. But this warning is not as serious as other warning because it just means that the trajectory you generate does not have a U-turn when it hits the maximum tree depth. But it does not impact the underlying algorithm of generating the MCMC sample. And if this is the only warning you get, then in your effective sample size and the R-hat diagnostics are all good, then you should be fine. Don't worry. The second warning is a second diagnostic metrics is the report of the divergence. And you can see here for this model, we do detect the divergence. The divergence happens when the approximation of the trajectory that follows Hamiltonian Monte Carlo carries large error. And this is a sign that maybe the curvature of the posterior varies a lot, or the posterior is very hard to learn by MCMC by Stan. And usually, Stan will provide some guides about how to avoid or how to eliminate those problems. For example, you can increase the adapt delta, to be closer to 1. But if it does not work, maybe we need to do some diagnostic, graphical checking to find a way to reparameterize our model or improve our model to avoid those divergence. But if it's in a early stage, we just want to fit a short MCMC chain and we only observe several divergence, it should not be a great concern. We can just run a longer MCMC chain to get a better inference, a more reliable inference. Next is the FBMI. This like measures how good the approximation of the tail of the posterior is. And if the FBMI is just slightly below the threshold, then the posterior is also like likely to good for the sanity check, but probably still not good for the final like reliable posterior inference. The last two diagnostic metrics are the effective sample size and R-hat. These two diagnostic metrics are the most commonly reported metrics we use in like scientific paper. The R-hat here like measures the convergence through comparing the between and within chain like estimates for parameters and other univariate quantities of interest. The R-hat is theoretically, R-hat is always greater than or equal to 1. But in practice, some like user might observe R-hat less than or equal to 1. R-hat lower is smaller than 1 is not a concern. Only a large R-hat is a concern. If we just in the early stage of our data analysis, R-hat below 1.1 should be sufficient. But if we want to get the precise posterior inference, the recommended R-hat should be less than or equal to 1.01. The effective sample size shows you like how many independent samples your MCMC chain is equivalent to. STAN provide both the buccal effective sample size and the tail effective sample size. The buccal effective sample size estimates the sampling efficiency for local summaries, such as mean and median. And the tail effective sample size computes the minimum of the effective sample size for the 5% and the 95% quantiles. If you want to check the R-hat and the effective sample size for each parameters, you can use the print method. Like as we've seen in the warning message provided by STAN, this with our current model, STAN reports divergence. But here I provide a link of a case study for this 8 school, and in this case study, the authors illustrate another parametrization that can solve the divergence warning issue. And this is, yeah, the reparametrization is called non-centered H-school implementation. And in my folder, in the STAN folder, I provide the STAN program for this non-centered H-school model. The command standard package provide a more diagnostic tool. You can use the sampler diagnostics method to check the how many iteration to check the tree depths for each iteration, and check to how many divergence it happens for each chain. And you can also use the diagnostic summary to get a summary of those diagnostic metrics for each chain and check the warning message. Apart from the command stand R, there's also very useful function that can be used to provide additional diagnostic and the summary statistics. Here I used the Bayesian plot in the posterior. Yeah. And the summaries method can provide a summary of the summary statistics like mean, median, quantiles, R-hat, and effective sample size. We can also select the specific parameters of interest and the summary statistics we are interested in to present the result. The drawer method can be used to extract the posterior draws, and with the posterior draws, we can generate the histogram of our posterior jaws through MCMC histogram. We can also generate MCMC trace plots through MCMC trace. And this MCMC scatter provides the scatter plot of our posterior samples. And in this plot, I highlight the iteration that observes divergence by green. And the last is the MCMC pair. This MCMC pair can show you pairwise scatter plot in the marginal histogram. At the end of this HTML, I provide more resource for the beginner of STEM. Like in the STEM homepage, there are a lot of resource, you can get the STEM users guide, STEM language reference memo, and also some tutorial about STEM. And I find the case studies provided by STEM to be a very useful resource, because in this case study, we can find others code for some specific problem. For example, if you search my name, you'll find that I wrote a case study for STEM around 5 years ago. And here I provide the functions I use to define my own log posterior density. And if we still have bugs that we cannot solve by ourselves, we can post a question on the STEM forum. The STEM forum, maybe I can show you some of them. This one, anyway. Yeah, you can see people's people post questions about their code and asking for asking for help from experts in STEM development team. And yeah. So in general, the best way to learn STEM is to start by working through some of the tutorial and example provided by STEM website, and then practice it by working on your own project. And that's pretty much everything I want to cover in today's seminar. And thank you for your attention. Any question?
Seems like there's a lot of tuning parameters.
Yes. Yes.
Yeah, but how many of these are actually settled? Things that the user can change?
I think all of them can be changed by user.
Mhm.
Yeah. What STEM did is to minimize the effort for user to tune their tuning parameters.
Right, but that implies that the user has some idea of the tuning parameters.
Yes, correct. We need to know what the tuning parameters do in the MCMC sampling algorithm. And it's also tricky because sometimes STEM do transformation, but STEM will not inform the user which transformation it used. It's documented in STEM user guide. But if we set up, say, the metrics in the parameter space that we believe the MCMC sampling happens, but actually STEM use transformation to transform the space to another space, then maybe there will be some unexpected result. So there are a lot of work to tune a MCMC algorithm. Yeah, as far as I know, STEM might scale your predictor before doing the MCMC fitting. For example, if the design matrix you input into STEM has like very different like variance for each column, then Stan might do some pre-processing to kind of generate a kind of standardized design matrix, and then sample with the standardized design matrix. And at the end of the sampling, Stan will transfer those samples to the like original space. And there are a lot of underlying algorithms. But all those algorithms are designed to accelerate the MCMC sampling algorithm. But once it does not work, it needs a lot of effort to figure out why.
So you worked with this 5 years ago. Who developed Stan initially?
Andrew Gelman, and his team. He's the leader research scientist in Stan development group. And also Bob Carpenter. He's also one of the supervisor when one of my supervisor when I was a postdoc at Columbia. So Dave, do you have any question?
Yes, actually, I guess several questions just in terms of, most of what I've done before has either been in bugs or JAGs type of framework. And one of the reasons is just the flexibility of writing that. And I just wonder if there's a comment that you could make about just writing your own log posterior, right? That's where the flexibility comes in.
Yes.
If that is relatively straightforward in your experience, or how complicated that is, because
that's a very good question. I believe I can interpret the flexibility in two aspects. The first is how convenient it is to define our like user-defined like functions, user-defined log likelihood. In my understanding, I think it's much easier to code in C++. Yeah. And I don't think the learning curve is that hard. But if like if you really can't like debug your code, then post a topic on the Stan forum, and you will get a lot of help from very excellent expert in Stan development team. A second aspect is like how flexible can we like select the MCMC sampling algorithm, because there are a lot of different type of MCMC algorithm, and people might want to try like a combination of Gibbs sampling and HMC. But unfortunately, this hybrid sampling algorithm is not available in Stan. I know there's a package called Nimble, and Nimble can do a hybrid MCMC sampling algorithm. It can combine the Gibbs sampling with HMC. But in my impression, I tried a Nimble and my code does not work very well. So I don't know how it works now. I can just tell you based on my experience. I think Nimble might not be as efficient as Stan based on my research experience.
Okay.
Yeah.
I mean, that was going to be my follow-up question is, I guess, given the same model, what is more computationally efficient, I guess, and yes, it'll be probably specific to the model and the, the MCMC algorithm used and what have you, but in your experience, a model in JAGs, Nimble, Pi, MCMC, all, there's basic hierarchical models can be written in all of those, right? Fairly easily. And in terms of just computation, how does it Stan compare to all to some of those other common ones?
I think for the most common models, Stan should be in general faster than Winbugs and the JAGs. But when there exists conjugacy or conditional conjugacy, sometimes Gibbs sampling is more efficient than like HMC. It really depends on the structure of your posterior, like how the posterior looks like, what's the geometry features of your posterior. I think maybe like if it's easy for you to code in JAX, then start with JAX. If it fails, then we you can try Stan. But Stan is also a very good starting point if you want to fit a arbitrary like Bayesian models.
Mhm.
And I think another benefit of Stan is that many people use Stan, and they provide a lot of like valuable discussion about why like the NCMC sampling fails on how to improve it. So even if you feel like the NCMC sampling in like Stan is very like slow, like after coding your model in Stan, I believe you will have a much better understanding of your own model, and you will have a better idea of how to improve your model. Yeah.
Great, thank you.
Okay, thank you. Thank you for attending today's seminar.
There any other questions?